All right, today we're going to dive into one of the most powerful ideas in all of electronics. It's called resonance. And honestly, it's the hidden harmony, the secret sauce that makes our entire wireless world work.
So, have you ever really thought about this? You're in your car and you're just getting bombarded by thousands of radio signals, right? All these different frequencies are hitting your antenna at once, and yet you just turn a little dial and somehow you lock onto one single crystal clear station. How in the world does a simple circuit pull off that kind of magic?
Well, believe it or not, the secret has everything to do with a simple playground swing. Yeah, you heard me right. The physics that lets a kid soar higher and higher is the exact same principle that lets your radio pick out that one station. It sounds kind of crazy, but let's break it down.
Okay, so you know how every swing has its own natural rhythm, right? Its own back and forth timing. If you just walk up and give it one shove, it moves a little. But what if you time your pushes perfectly with that natural rhythm? Each push adds more and more energy, and suddenly that swing is going way higher. That is resonance. You've found its special frequency and you're amplifying it.
Okay, so that's a swing. Let's take that exact same idea and bring it into the world of electronics. What does resonance actually mean inside a circuit?
Well, in a circuit, resonance is this one special frequency, this magic number, where its two key players, the inductor and the capacitor, basically have a showdown and cancel each other out. You see, they have totally opposite reactions to frequency, and at that one perfect resonant point, their opposing forces just, poof, disappear. The circuit suddenly acts like there's nothing there but a simple resistor.
So, to really get this balancing act, you've got to meet the team. We've got our dynamic duo and their trusty stabilizer.
First up, you've got the resistor. Think of it as the stabilizer, the calm one in the group. It just kind of dissipates energy. But the real drama, the real action, is between the inductor and the capacitor. And here's the absolute key. They are total opposites when it comes to frequency. An inductor, well, it hates change. The faster the signal changes, the higher the frequency, the more it fights back. So its opposition, what we call impedance, goes up. The capacitor? Totally different personality. It loves high frequencies. The faster things change, the easier it lets current pass. So its impedance goes down. So you've got one whose opposition goes up with frequency and one whose goes down. You can probably see where this is headed, right?
Okay, so let's put them all in a line, what we call a series circuit. This is where we see our first type of resonance, and it's all about getting the absolute maximum flow.
So imagine we're turning a frequency dial. As we go up, the inductor's opposition is climbing and the capacitor's opposition is dropping. And at one very specific point, boom, they perfectly match. The inductor's push equals the capacitor's pull. They become equal and opposite, and they completely cancel each other out. It's like they just vanish from the circuit's point of view. That's it. That's the resonant frequency.
So what happens right at that magic moment, at that resonant frequency? Well, since our two opposing players have basically taken each other out of the game, the only thing left putting up any fight at all is that simple little resistor. That means the circuit's total opposition, its impedance, plummets to its absolute minimum. And when you have minimum opposition, what happens to the current? Well, it goes to its absolute maximum. It just skyrockets. The circuit throws open the floodgates. But here's the kicker. It only does this for that one specific frequency. For everything else, it's still a tough path. That's why we call a series resonant circuit an acceptor circuit. It finds its favorite frequency and says, yep, you can come on through.
And that right there, that ability to accept just one frequency, is the absolute heart of how we tune into things. But how picky is it? How can we control how sharp that tuning is?
That's where this idea of bandwidth comes into play. See, it's not just one single mathematical frequency that gets a boost, but a small range of frequencies right around it. If that range is super tight, we call it a narrow bandwidth. That means the circuit is very selective, really picky. If the range is wider, well, that's a wide bandwidth, and it's letting in a whole chunk of nearby frequencies.
And the way we measure how selective a circuit is with something called the quality factor, or just Q for short. All you really need to know is this. A high Q factor means you've got a really narrow bandwidth. It's like a laser-focused tuning peak, a very sharp or pointy response.
And this is exactly why Q matters so much. Look at this. A low Q circuit, it has a wide, sloppy, rounded peak. That's like a bad radio that picks up 2 or 3 stations at the same time. You just get a fuzzy, garbled mess. But a high Q circuit, that gives you a sharp, narrow, perfect peak. It zeroes in on exactly the one station you want and ignores all the others. And that gives you that crystal clear signal. Okay, so series resonance is all about maximum current, right? It's an open door for one frequency. But here's the plot twist. What happens if we just change the wiring a little bit? Well, that takes us to a totally opposite situation, minimum flow. So get this, we take the exact same components, but instead of lining them up in series, we wire them side by side, or in parallel. The basic idea that the inductor and capacitor cancel each other out at the resonant frequency, that's still true, but the final result, it gets flipped completely on its head. Let's just put these two side by side. It makes it super clear. With series resonance, at that special frequency, the impedance is at a minimum. It's like a superhighway for the current. That's our acceptor circuit. But with parallel resonance, whoa, the exact opposite happens. The impedance shoots up to its maximum. It's like a giant roadblock, just for that one frequency. So the current from the source drops to almost nothing. It becomes a rejector circuit. Okay, so we've got these two powerful tools, acceptor circuits that let one frequency through and rejector circuits that block one frequency. Why is this simple idea of opposites so important? Because really, this is the entire foundation of how we handle signals. Resonance is what lets us do two incredibly useful things. One, we can select a signal we want, right? Pluck that one radio station out of the air. Or two, we can reject a signal we don't want, like filtering out annoying noise. Every single piece of wireless tech you own, your phone, your Wi-Fi, you name it, it all works because of this beautiful principle. And this quote here really nails the other half of the story. The parallel circuit is a rejector circuit because its impedance is at a maximum. It's so important to remember it's not just about what you let in, it's about what you keep out. And sometimes building that perfect wall is just as powerful as building the perfect door. So when you boil it all down, resonance is really just about tuning in. It's about finding that one specific signal, that one frequency you care about, and making it louder than all the background noise. And that kind of makes you think, doesn't it? In a world that's just full of signals and noise and distractions, what other parts of our lives could really use a better filter?